Thanks everyone for tuning in. It's my pleasure this week to introduce Dave Aasen, physicist and also a mathematician, I guess, he's pretty good at the two, which is rare. So Dave actually did his bachelor's in Canada at McGill, right? Did a joint in math and physics at McGill, and then moved on for a PhD at Caltech under Jason Alicea. He studied various aspects of topological phases, especially fermionic topological phases and all the beautiful mathematical structure that arises in the classification and understanding of those quantum states of matter. And after his PhD, he moved on in 2018 to Microsoft Station Q, which is in Santa Barbara, as a postdoctoral fellow. And that was a joint position with the Kavli Institute, KITP, in Santa Barbara. And I just learned that Dave will be a permanent staff at Station Q. Congratulations. And today, we'll hear about characterization and classification of symmetry and enriched fermionic phases. So Dave, the floor is yours.
Yeah, thanks, Will. Thanks for the kind introduction. Hopefully everyone can see my mouse. Maybe Will.
Yes.
Great. Yeah. So it's a great pleasure to be here. Thank you very much for inviting me. I really like talking about this work. This work is somewhat technical, so I'm not going to give any derivations, but hopefully give you guys a sense of the ideas and computations that went into it. Feel free to ask any questions at any point. I'd be happy to clarify anything I can. So that said, the talk is about characterizing and classifying fermionic phases in the presence of symmetry. And we're going to be using the sort of algebraic techniques of G-cross braided tensor categories. So I'll need to sort of describe what those are and how they relate to the physics and so on. So this is a rough outline of the talk that I presented here. After a few slides of introduction, I will describe what the algebraic description of fermionic phases in the absence of symmetry, and then discuss how we start including more and more structures of symmetry into these topological phases. So starting with global symmetry action, and then how the global symmetries localize on particles, and then how we introduce external symmetry defects, and then ending with the full classification and algebraic description of these phases. Now, this work could not have been done without my two collaborators, Parsa Bonderson and Christina Knapp, who are also both at Microsoft Station Q. And the whole talk is based off of these two works. This torsorial action on G-cross braided tensor categories is more of a mathematical work, but really is what allowed us to solve many of the problems in this fermionic classification. So it allowed us to very efficiently and quickly come up with examples and use that in order to sort of single out the ideas that we needed in order to properly characterize these fermionic phases. Okay, so with that, let me begin with the introduction. So today I'll be talking about topological phases, and we'll be focused on topological phases in two spatial dimensions. So you should imagine that there's some manifold in the background that we put our phase on. Maybe it's a torus like I've shown here. And then sitting on top of that manifold, think of as a graph. So it'll have phases, vertices, and edges. We'll describe a Hamiltonian, which is a Hermitian operator. It's actually a sum of local Hermitian terms, which is local with respect to this graph, or if you like, with respect to the Hilbert spaces that we assign to various components of this graph. So in this case, I've assigned a Hilbert space to each vertex of this graph, and the total Hilbert space is the tensor product over these local Hilbert spaces, and the Hamiltonian is just some Hermitian operator, which is a sum of local terms acting on this Hilbert space. Okay. Now we'll be interested.
Are they finite dimensional?
And it should be finite dimensional. That's right. Each local Hilbert space will be finite dimensional, and we'll only ever consider graphs that have finite vertices. Although in reality, we are interested in the thermodynamic limit, but I don't want to get into those subtleties in this talk. Did you have a further question or comment?
So finite number of vertices and finite dimensional Hilbert spaces.
Correct. Yeah, soon we won't be talking about Hamiltonians at all. So. All right, moreover, we will be interested in a special subclass of Hamiltonians, which are gap. meaning there'll be a finite separation in energy between the lowest lying state and the first excited state. So if you're a mathematician, the ground state is the smallest eigenvalue or most negative eigenvalue of the Hamiltonian. And then we only want to consider Hamiltonians which have a finite gap to all other states, so finite separation, that is preserved in the thermodynamic limit. So as we add more and more vertices to this graph. So in such a scenario, we would also like to consider a scenario where the excitations are defined by sort of local blobs of energy. So it'll be local blobs of energy that sit on the surface, and we'll characterize them in terms of emergent topological quantum numbers. So these will be super selection sectors, and I'll describe that a little more carefully later on. And those emergent topological quantum numbers get identified with the low energy effective theory describing this phase of matter. And that will be a topological quantum field theory, which today will be described by a unitary modular tensor category. I'll also explain what that is in a few slides. Okay, so now let's think about the set of Hamiltonians that we have. So without, and we're going to first start without symmetry and then ask what happens if we add fermions or add symmetry. So without symmetry imposed, gap phases are fully characterized by topological order, meaning each phase of matter is a collection of Hamiltonians whose low energy effective theory that we're interested in, and that low energy effective theory is described by completely characterized by an algebraic piece of data called a unitary modular tensor category, along with a chiral central charge. All right, so if we wanted to think about a cartoon for the phase diagram, it might look like the following. So we have Hamiltonians, which are points in parameter space, and we consider two Hamiltonians to be in the same phase if they can be continuously connected without closing the gap. And then we label the region in that phase space by some unitary modular tensor category, C, which captures the low energy degrees of freedom of every one of those Hamiltonians in this region. All right, are there any questions about that? Now, what about bosonic versus fermionic phases of matter? Well, at the microscopic level, meaning Hilbert spaces and Hamiltonians, it's very easy to distinguish the two. A bosonic topological phase is built from bosonic Hilbert spaces, so just tensor products of C to the n, whereas a fermionic Hilbert space is built from tensor products of supervector spaces, which I've used the notation CP/Q here, which stands for P even fermion parity vectors and Q odd fermion parity vectors. And when you tensor these Hilbert spaces together, you have to worry about causal signs, so that if you interchange odd vectors, you pick up a minus sign, for example. And the difficulty of characterizing fermionic phases really amounts to figuring out how this supervector space embeds into our algebraic description of the low energy effective theory. And we'll get into more details on that in just a little bit. The second axis of complication that we're going to consider today is what happens when we add symmetry to the problem. So of course, not all Hamiltonians are symmetric under every group. So certain parts of parameter space are going to be thrown away. And moreover, the way that symmetry is realized on a particular phase may happen in different ways. So that's what I've tried to represent by this diagram on the bottom here. Each region that was labeled by C previously is still present. And then there's a finer grain classification which tells you about how that symmetry is realized within that phase. And we label the resulting algebraic description or low energy effective theory by something called a G-cross braided tensor category. And again, I'll talk about much more detail. I'll give you much more detail about what that is, again, in just a little bit. Okay, and we'll refer to those as symmetry enriched topological orders if we're just thinking about bosons, or fermionic symmetry enriched topological orders if we're thinking about fermions.
Too soon to ask for some concrete illustrative example?
Yes, I will give a few though. But if you're yeah, I will give a few in just a bit. So if you want, I'll give a few in several slides. So the answer is yes, it is too early. Okay, so yeah, let me briefly mention the previous work on symmetry in fermionic theories. So it was mostly focused on fermion SPTs, which are, you know, sort of the most simple kinds of symmetric fermionic theories that you can construct. And they were developed in sort of in three different ways, but these all turn out to be equivalent. So there's something called the defect decoration, which is a procedure for generating fermion SPTs where you build symmetric configurations of domain walls and dress the domain walls with lower dimensional invertible fermionic orders. Another approach pioneered by Danfried and Kapustin and others is using the Pontryagin dual of the spin-Bordism group. And then the last way that previously was considered was thinking about G-graded fusion categories, which actually turns out to be very closely related to this defect decoration approach and also closely related to this Pontryagin dual of the spin-Bordism. Now, drawbacks of these three approaches is that they don't tell you, at least not in a simple way, they don't tell you any information about the excitations in the theory. You know, what is their braiding or fusion or any of these properties that we may have access to in an experiment in principle. So what we did actually goes beyond this in two ways. So one is, you know, we describe all the properties of the excitations, their fusion, braiding, and so on. And we also go beyond fermion SPTs. We construct general non-invertible topological orders as well. And that's going to be the main bulk of this work, or main bulk of this talk. We'll be discussing sort of the complications that appear when you do that. Okay, so simultaneously to our work was, you know, these sort of five, I'll say concurrent works that all appeared at the same time or around the same time. 4 of these 5 works came out of Mason's group. So these first, well, this first one by Mason and second one's by Gu's group, where they study symmetric invertible fermionic orders. And then there was 3 more by Mason's group, 2 studying symmetry fractalization and anomalies in fermionic phases. And this last one is just purely about anomalies of fermionic phases. So all this work is very interrelated. These 3 topics also appear in our papers. So we, and I'll discuss today. Today, I'll mostly focus on the symmetry fractalization and anomalies aspect. And if I have time, I'll mention the work we did on symmetric invertible fermionic phases. Okay, so with that, let me get back to my outline. So that was the introduction. And yeah, the rest of the talk will sort of be following this path of arrows. So we'll start by describing more of the algebraic properties of bosonic and fermionic phases, and then discuss how we introduce symmetry into the problem, and then how that symmetry localizes on the particle. That's some defect, how we use external symmetry flux, finally the full classification. Are there any questions as we understand them through the lens of unitary modular tensor labeled by character C here? So you think of C as a data that appears in that list are the set of anyons in our theory, or topological charges, as I'll often refer to them. So you should be thinking of a 2D piece of material. Inside that 2D piece of material, we can have our anyons, or these topological charges, and they carry labels A and B, which are part of the defining data of this unitary modular tensor category. And if you like, the more sort of intuitive definition of an anyon is that it's a local excitation, so a local blob of energy, which cannot be made locally. So that will be what it means for it to be a non-trivial anyon. All the trivial anyons are any particle or object that you can create locally. All right, so the first piece of data that goes into C is just this list of anyons that we have in our system. All right, Now we can start doing things to those anyons. We can push them together and find new anyons. We can split them apart or pair create, braid them, and so on. And the rest of the data in this unitary modular tensor category tells you how to keep track of that. So the second piece of data we'd be interested in is what happens when you bring two anyons together. So in this diagram, I have A and B, and I just imagine slowly pushing A and B together. And then I can do a local measurement and see what that composite particle, the composite of A and B, looks like in terms of the simple objects or the anyons of this theory. And that's what these coefficients NABC represent. They tell you when C can appear from a local measurement of A and B, and NABC, which is an integer, 0, 1, 2, and so on, tells you the number of distinct ways in which A and B can fuse to C. All right, so now when we build our Hilbert spaces, we can imagine all configurations of anyons being created by starting from the vacuum, splitting that into a particle and antiparticle pair, and then so on and so forth. And so the way we keep track of this is using these trivalent fusion spaces, which I've drawn at the bottom of the slide here. So on the right, I have a picture which shows a C anion splitting into A and B. And these indices, this index nu takes values from 1 up to NABC. And similarly, on the left, I've shown this fusion process where A and B fuse into C. And if you like, you can think of this as a space-time diagram where space is on the horizontal axis and time is on the vertical axis. And as time goes along, A and B literally fuse into C. So now we may have multiple ways of creating the same vector space. So this fusion space of 3 particles, A, B, and C fusing into D, can be decomposed in 2 different ways. So one is shown on the left side here, where A and B first fuse to X, and then C with X into D. And the other is shown on the right-hand side, where B and C first fuse to Y, and then A and Y fuse to D. All right, since we're doing quantum mechanics and we have 2 ways of decomposing the same Hilbert space, we know they should be related by a unitary transformation. And that unitary transformation is called the F symbol. So this F symbol is labeled by the anyons on the external legs of this diagram, and its indices are the internal objects that label the distinct vectors in this fusion space, in this case, X and Y. Okay, now these unitary matrices are not arbitrary, they're actually highly constrained. And the constraint is called the Pentagon Equation, which is shown at the bottom here. And this represents 2 distinct paths of diagrams that get us from one place back to the same place. Yeah, as shown here. Okay, so that's some equation that when you write it out in terms of these F symbols, looks like FF equals FFF. And in order to have a consistent theory, it must be satisfied. Okay, similarly, we can take a pair of anyons and braid them around one another. And the corresponding symbol that keeps track of that is called the R symbol, which you can also just think of as a linear relation on these 2 diagrams that I've shown here. And that R symbol is also subject to a consistency condition, which is known as the hexagon equation. And the mnemonic for the hexagon equation is RFR equals FRF. Okay, so that's just a consistency condition between associativity and braiding. All right, so if we, just to recap, if we want to come up with one of these unitary modular tensor categories, we first list out the anyons or charges that we're interested in. We postulate a set of fusion rules, and then we go and try to solve these 2 sets of equations. If we do that successfully, then we have a braided tensor category. And the last condition we need to impose is this modularity condition, which just says that every anion must be remotely detectable by some other anion in the theory. Meaning if we do a full braid with this other anion, we should pick up a phase, and we should be able to detect all of the anyons in this way. Okay, so that's the end of my review of bosonic topological phases in the absence of symmetry. Now I'm going to describe how we think about fermionic phases also in the absence of symmetry. Okay, so just to remind you, our Hilbert space is the tensor product of these local Hilbert spaces. And we have two options. Those local Hilbert spaces can either be bosonic in nature or fermionic in nature. And so the name of the game now will be to understand how we can embed this fermionic Hilbert space, or the local fermion of our theory, into the algebraic description. All right, now there are two algebraic perspectives for describing fermionic topological phases that I'm aware of. One is to take a bosonic theory, such as the one that I just described, that has a fermion in its spectrum. So it has some, one of these anyons that appear in that list is actually a fermion. We interpret that object as a physical fermion, and we identify it with the odd parity vectors sitting inside the supervector space. So that's option one. The second option is to take a bosonic theory, again, like I just described, and then enrich it in the category of supervector spaces and spin structures. And this might be referred to as a superpivotal braided modular tensor category. That theory is not yet developed, so we're not going to talk about it, and we'll take this first approach, which is what we developed in our paper. All right. So what is that first approach? Well, okay, so whenever I'm talking about a fermionic theory, I'll use M rather than C. So M stands for fermionic modular tensor category, and I'm going to now describe to you sort of the properties of that fermionic modular tensor category. So to start, it is a modular tensor category. And then the first condition that we impose is that it has a fermion, so this thing called psi, and we'll identify that with the physical fermion. Okay, so what is a fermion? Well, in this context, this is the definitions. So if I take two fermions and I braid them, I pick up a minus sign. That's this sign here. Is there? I should ask if there are any questions.
May I ask a question? Yes, I'm just curious. Can you, if I try to realize your unitary modular category through a Chern-Simons theory, bringing a fermion, is it coupling it? Is it coupling the Chern-Simons field to a fermion? Is it as naive as that?
Yeah, so I'm actually not an expert at Chern-Simons theory or how you think about fermionic theories from that perspective, but I believe you would need to couple it to a spin structure in some way. I know there is literature on this that I could send to you.
It's just that you can realize your UMTC through Chern-Simons. It's Chern-Simons theory is universal as far as I understand. Yes. So there should be a picture. And yes, I was just curious about there is.
Yeah, I think so. The most naive thing is you can use so let's suppose any modular tensor category can be realized through a Chern-Simons theory. Then the thing that I'm calling a fermionic modular tensor category would be any Chern-Simons theory that has a fermion in it. At least that's where we're at this point in the talk.
Okay, thank you.
Yeah, okay. Just to clarify, so do this braiding is related to the R metrics from your definition of MTC?
Yes, absolutely. Yeah, this minus sign here is just R superscript psi.
So the R is basically a scheme. Okay, good.
Yeah.
But okay. Dave, for the fermions in Chern-Simons, like FQH states, fractional quantum Hall states, like Laughlin 1/3, it's described by some abelian Chern-Simons, and I guess you don't need to really couple it explicitly to a fermion, but the Chern-Simons level.
So if you do that, do you end up with a pre-modular theory that has a fermion in it?
If you do that, you end up with the right description of the fractional quantum Hall effect killing 1/3. So then I guess, you have trivial fermion in there.
You have a fermion that braids trivially with every anion in the theory, right?
Yeah, because if you think about the partons, you have, E/3 charged partons. If you take 3 of them together, you have a charge E fermion. So, but the Chern-Simons description seems to be okay with just the gauge field, the abelian gauge field.
Yeah, but I think, well, so there's a problem if you ignore the vortices, which is, you know, for example, well, one, you're missing the vortices, and two, you can't do, you miss out on certain states on the spin torus, like you just won't have any states that you can assign to the non-bounding spin torus.
So the question is, what is a spin torus?
What is a spin torus? Just a torus with spin structure. Yeah, I feel like we're going to go in a bit of a tangent.
Yeah. So I mean, it was a comment. Yeah, please continue, and we can talk about this later. Sorry.
Sure. Yeah, absolutely. Okay. So yeah. So just to clarify, we have a modular tensor category M. It has a fermion sitting inside of it. That fermion has these statistics, meaning if I braid it with itself, I pick up a minus sign, and it has Z2 fusion rules, meaning if I fuse the fermion with itself, I get the vacuum. Okay, so what this immediately tells you is that every topological charge in our theory either braids trivially with the fermion or non-trivially. Okay, if it braids trivially, we will call it a quasi-particle. If it braids non-trivially, we'll call it a vortex. And that's, I'll also add subscripts to the topological charges, X here, which tells you in which way it's braiding with psi. Is it transparent to psi, or does it pick up a minus sign? All right, so what this tells us is that every modular tensor category with a fermion is actually Z2 graded into one component, which is a supermodular tensor category and only has objects which are transparent to the fermion. And the other component is the non-trivial Z2 grading, which has all of the vortices. So every object in M1 braids non-trivially with the fermion. Okay, and I believe the description Will was just giving was a description of M0 for some theory. And if you want the full theory, you should do this minimal modular extension to include the vortices. But we can discuss more later. Okay. So it was shown by these folks that if you have so another way to look at M is to think about starting with a supermodular tensor category and then building a minimal modular extension, namely adding vortices to it so that you end up with a modular tensor category. And what these people proved was that if you have one minimal modular extension, then you can in fact find 16 distinct choices. And I'll give a justification for that momentarily. Okay, so then when you do your classification of these fermionic phases, there are two ways that you can go about this. One is to start with a fixed supermodular tensor category and then add structure from there. So extend to a minimal modular extension and then add symmetries. Or we can take M as our starting point and add symmetry to that. So I'll describe both of them later, but I will focus on the former, where we start with a supermodular tensor category and build the minimal modular extension and then add symmetries. So now I'm going to give some examples. Are there any questions about this slide before I move on, or anything at all? Okay, great. So a very important set of examples for fermionic phases are the invertible fermionic orders. And an invertible fermionic order is defined in the following way. So the quasi-particle sector only has the trivial particle, the identity or the vacuum, and the fermion, which I'll call psi 0. And then in order to get the full fermionic modular tensor category, we need to add vortices to the theory. And so as mentioned on the previous slide, there are 16 ways to do this. And I'll sort of characterize them just in a second. Each theory will be labeled by this nu, which is related to central charge by division by 2. And all 16 of these theories are distinguished by the topological spin of their vortices. So their vortices all have the same topological spin within a given theory. And that topological spin, which is the eigenvalue under a 2 pi rotation, distinguishes which of these nu we actually have. Okay, now what do those theories look like? I'm not going to give a complete description. Their quasi-particle sectors all look the same. They're all just trivial particle and a fermion. Their vortex sectors look like the following. So they either have one non-abelian object, which I didn't describe what that was, but it's related to these Majorana zero modes or Ising topological orders, if you're familiar with that. And half the theories are of this form. So if nu is 0 mod 2, you have this so-called Ising-like theory. If nu is equal to 0 mod 4 or 2 mod 4, then the vortex sector splits into a pair of abelian vortices, which I've labeled I subscript 1 and psi subscript 1. And together with the quasi-particle sector, the fusion ring is either Z2 times Z2 fusion rules, meaning the fusion ring forms a group, and this is the group that you find, or it's Z4 fusion rules, if nu is equal to 2 mod 4. So those are one set of examples, and we'll encounter them a few times throughout the talk. So another property that fermionic phases have is so-called stacking, and I'll describe this in the context of invertible fermionic orders on this slide. So if you have 2 fermionic phases, in reality, you can bring those fermionic phases closer and closer together, and eventually the fermions sitting in phase 1 can tunnel into the second layer into phase 2. So we needed a way of saying how we identify fermions across different topological orders. And the right mathematical description for this is so-called condensation. So the object you want to condense or fluctuate over your system is this composite particle of a fermion from layer 1 and a fermion from layer 2. And what that does is identifies the fermion from layer 1 with the fermion in layer 2. When you do this, you are guaranteed to find another fermionic modular tensor category. And if you were to go through this computation, which is actually quite technical, what one finds is that these nu and nu prime are additive modulo 16 under this condensation process. Now this operation is defined for all fermionic modular tensor categories. They didn't have to be the invertible ones. And you're always guaranteed to find another fermion MTC after you do the condensation. So you can think of this as a product on the set of fermionic phases. Now, moreover, this product is commutative. So it's symmetric in whether or not, it's symmetric in interchanging these 2 layers. And it's also associative. You can you can stack phase A with phase B and then with phase C, or you can stack phase B with C, then with phase A. And physically, what that tells you is that there is essentially a unique way to identify fermions between different 2+1D fermionic topological orders. All right. Now, the last thing I'll say on this slide is that the nu equals 0 theory plays a special role. So if we stack K0 with K0, we get K0 back. So K0 plays the role of the identity element in the set of fermionic phases. So yeah, I guess I didn't write it, but if I replace K nu prime with any other fermion MTC and K nu with K0 and do the stacking, I'll find that other FMTC back. So it really does act as the identity element under stacking. That's the end of my brief description of fermionic topological phases. And what I'd like to do now is discuss how we introduce symmetry into the problem. So I'll first start with bosonic phases and first thinking about how the symmetries act on the particles and then the states. Okay.
Dave, so the invertible one, that excludes like FQH at filling 1/3, for example, right? I mean, this is not...
Correct. That's non-invertible.
And will you discuss the class of fermionic topological systems that includes the
Non-invertible?
last line? Yeah.
Yeah. So everything I say, so these were just an example. So the nu equals 1/3 Laughlin state is a super modular tensor category. You would need to build this minimal modular extension of it, which, okay, we can do that. And then everything I say will apply to this, super MTC with minimal modular extension. So I won't give the examples, but I'll discuss like the anomalies that you will encounter when you look at those theories.
Perfect.
Okay,
Thanks.
Great. Yeah, so, and just to reiterate, like here you would just replace M0 with a set of topological charges appearing in your, okay.
Oh, sorry, can you briefly clarify why your root of unity in the topological quantum field theory must be, 16th root of unity?
For the invertible fermionic phases?
Yes.
Yeah, so I'm not sure. Yeah, so what you can do is write down all of these fusion rules and check that those are the only possible fusion rules you can get for a minimal modular extension, namely one whose total dimension of the M1 sector is equal to the total dimension of the M0 sector. And then you can just compute all the consistent braidings, so R matrices and F matrices on that set of theories. And you'll find that the topological spins are all fixed to a root of unity of this form. So I don't know if that actually answers your question, but that's what you find. And I have the wrong reference here. This should be Kitaev's 2006 paper where he goes through exactly that calculation I just mentioned. There's some rigidity in these theories, so you can't choose some phases. You cannot choose arbitrarily. For gauge non-invariant phases, those you actually do have an arbitrary choice for. So now let's talk about topological symmetries. So at its most primitive level, it is a permutation of the topological charges. So here I have my 2D piece of matter. It's got anyons A and B sitting here. And the topological symmetry, which I'll denote as phi, just applies a permutation to those objects. Namely, A maps to phi of A, which is another object in my theory, and B maps to phi of B, which is also another object in the theory. And it is constrained to leave the vacuum unchanged. Okay, for a fermionic topological symmetry, it's more or less the same thing. It, again, just applies permutation to the objects. And I'll use this superscript F for fermionic topological symmetries. So it permutes the objects in a similar way. B goes to phi of B, A goes to phi of A. But it's constrained to leave the physical fermion fixed. So psi must map back to itself. Okay, and one way you might justify this is by thinking about your fermionic phase as living at the boundary of some higher dimensional fermionic phase for which the symmetry doesn't act on. And we should be able to move the fermions on and off of this phase. And because of that, the symmetry has to act trivially on the fermion. All right. Now, one important topological symmetry that is in every fermionic modular tensor category is the following. So if I take the quasi-particles, namely things that braid trivially with the fermion, this particular topological symmetry does nothing. If I take the vortices, I fuse the fermion with them. So let's summarize by this equation. V of A sub x maps to psi to the power of x tensor A sub x, where x is either 0 or 1. And when I have a 1 in this exponent, it means I'm tensoring with psi. Okay, so that's how symmetries act on the charges. What about the quantum states? So all quantum states can be built out of these trivalent fusion spaces. So I just need to tell you how the symmetries act on that trivalent fusion space in order to figure out how the symmetries act on any state in the whole system. All right, so when I act with phi on this trivalent fusion space, I'll find the external legs are permuted as they're shown. So C maps to phi of C and so on. But we are allowed to pick up an arbitrary complex number, which in general can be a matrix if you have fusion multiplicities, multiplying the state that we end up in after we apply this topological symmetry. Now, those u's that are multiplying the state are not arbitrary, but have to satisfy the consistency condition that I've shown at the bottom of the slide here. So we should be able to associate and then apply the symmetry, or apply the symmetry and then associate and find ourselves at the same result. All right, are there any questions at this point? All right, moreover, we will add an equivalence relation on our topological symmetries, which are defined by the fermionic natural isomorphisms. So we'll say two topological symmetries are equivalent if they're related by this so-called fermionic natural isomorphism, which itself is a fermionic topological symmetry, but it acts in a very simple way. So it doesn't permute any of the anyons, and all it does is multiplies a diagram by complex phases, which are labeled by the external legs of the diagram. Okay. Now, for it to be a fermionic natural isomorphism does mean that it has to satisfy a local fermion constraint, that gamma psi is +1. Okay. All right. So now we will denote equivalence classes of topological symmetries with square brackets, equivalences under these fermionic natural isomorphisms. And if we consider the full set of fermionic topological symmetries, that forms a group which we've called aut f of m. All right, now what is the group operation? Well, it's just composition of the topological symmetries. So if I put square brackets around them, they'll compose just like a group. If I leave out the square brackets, then they compose up to a fermionic natural isomorphism. All right, so now that we have the fermionic topological symmetry group, we can use that in order to construct G-symmetric fermionic phases. All right, so the starting data will be this global symmetry G. We'll also have this additional fermion parity symmetry, which is just saying the number of fermions in the system is conserved mod 2. And these two groups get put together in a way to form the full fermionic symmetry group, which I've denoted with a curly G here and superscript F. And if you like, that full fermionic symmetry group is a Z2 extension of G. Okay, and we'll specify that Z2 extension with the subscript W, which denotes a 2 cocycle. If you're not familiar with how you build extensions of a group in this way, just ignore W and set it to 0. Okay, so now we want to pick a symmetry action. And like I was mentioning earlier, we have a choice. We can either start with the supermodular tensor category M0 or M. And in this case, I'm going to start with M. So a symmetry action is going to be a group homomorphism from G into aut f of M. All right. Now, I say that, but I'm going to eat my words. It's not actually a group homomorphism. It's actually a projective symmetry action. So there's this sort of strange projectivity factor out front. I'm going to say that we just ignore this for the rest of the talk, but I wanted to warn you that it is there, and you'll find it discussed in our paper if you want to read more details about it. So for the rest of the talk, we'll assume that this is really a group homomorphism from G into aut f of M. This projective symmetry action is related to these non-trivial central extensions and special cases, and there's a lot of details there that I don't want to get into. Okay, so with that said, we pick a group homomorphism from G into aut f of M. All right, so now I want to start discussing the kinds of anomalies and obstructions that can appear in these fermionic phases. So for the most part, the rest of the talk will not actually be discussing the algebraic data of the theory, but rather obstructions to certain algebraic data existing that would describe our physical theory. And the first one that you encounter, and I'll always phrase the questions in the following way. I'll say, can we do something from something to something? So in this case, can we extend a symmetry action on M0 to M? All right, and the answer is not always. You encounter an obstruction to doing this, which we've labeled with this row here because it's an obstruction to finding a consistent symmetry action on M0 that extends to M. All right. Now, how do we actually compute this obstruction? Well, you look at the restriction of the set of topological symmetries on M to the set of topological symmetries on M0. If row 0 is not in the restriction of the symmetries from odd f of M to odd f of M0, then you're already out of luck. So let's assume that's the case. Then we pick an arbitrary lift from row 0 on odd f of M0 to odd f of M. And we ask, does that lift compose like a group homomorphism? So that's what I've shown over here. S is the lift from odd f of M0 to odd f of M. And generically, what you'll find is some 2 cocycle. So this is a function of 2 group elements, the group elements that we ask to compose like the group wants. And yeah, so generically that will be a 2 cocycle. And in the case where it is a 2 co-boundary is exactly the case where there exists a lift such that the lifted symmetry action composes like a group. All right. So that was a little bit technical. The physics behind this is if this obstruction doesn't vanish, so if it's a 2 cocycle but not a 2 co-boundary, i.e. a non-trivial cohomology class in H2 of G valued in Z2V, then your theory has to live at the boundary of some higher dimensional fermion SPT. All right. Oh, and in case some of the audience is not familiar with group cohomology, I'll just say anytime I have something that looks like H with a superscript n of G valued in some group, that itself is a group. So Hn of brackets always forms an abelian group. All right. So when these obstructions vanish, meaning when it doesn't have to live at the boundary of some 3 + 1 d fermion SPT, then we have a torsorial classification by H1 of G valued in Z2V. Oh, and I forgot to mention Z2V refers to it's a group Z2, and the topological symmetry that I'm referring to there is this special vortex commuting symmetry I mentioned a few slides back. Okay, so when this obstruction when this obstruction vanishes, we'll find a torsorial classification of our theories, which is given by changing our symmetry action by that special symmetry I mentioned earlier, V. And it turns out we can interpret that also through the stacking relation, which I mentioned earlier, stacking fermion SPTs. And I'll describe that in more details very soon. Okay. Are there any questions? I know that was a lot to digest.
I'll ask later.
Okay, sounds good. Yeah, I realize I should also move pretty quickly. Yeah, so yeah, let me speed up a bit. So yeah, so we have our phase of matter. We're trying to build a G-symmetric phase of matter. We've chosen our symmetry action on the phase itself. This is specified by rho. Now we want to consider how that symmetry localizes on the particles. So here I have some space sitting inside these regions are anyons. I want to consider acting with the physical symmetry, which I'll call R sub G. And R sub G will sort of vanish into space mostly all around, except near the anyons. There it will act non-trivially. And what happens is we'll pick up some phases or unitary, local unitaries, if you want to think about the microscopics, which I've labeled U sub G. And what the authors of this paper showed is those phases form a projective representation of the global symmetry group G. Okay, now it turns out not all global symmetry actions can actually be realized locally. There is an obstruction to doing that, and it's valued in H3 of G, valued in the abelian anyons. So A are the abelian anyons of our fermion modular tensor category that we're trying to build a G-symmetric version of. Okay, and the way you compute this O is from these natural isomorphisms that describe how these rows fail to compose like a group. So they will compose like a group up to fermionic natural isomorphisms, but they themselves will not actually compose like a group, and they'll have this extra factor kappa sub GH, which is a fermionic natural isomorphism. Actually, I guess here I'm talking about bosonic phases, so it's just a natural isomorphism. So when this obstruction vanishes, meaning when O is trivial in H3, or when O is a co-boundary, then we could find all other ways in which the symmetry fractionalizes on the particles via an H2 torsor. So there's a torsorial classification, which can be realized by just finding all the elements of this cohomology group here. All right, now what changes in the fermionic setting? Well, this is now a fermionic natural isomorphism. We can again view this as a bosonic theory and define the same invariant, but one finds that your torsor is valued in Z2 of GA modulo B2 of G A0, where A0 are the abelian quasi-particles. And you might look at that and think it looks a little bit strange. And indeed it is. If you have an H3 invariant, you would expect an H2 torsor, not a Z2 torsor. And I'll explain how that gets fixed when we change our perspective on this classification in the next slide. The other thing I'll mention is that these torsors, although I won't explain too much detail, these torsors, when they're valued in all of the abelian quasi-particles, all the abelian objects, vortices and quasi-particles, they can actually change this global symmetry group. And that's actually where the fix will come from. So if we fix our global symmetry group GF, then this torsor will not actually, this torsor will actually be valued in H2 of G in the abelian quasi-particles A0. So now, there's lots of obstructions that appear when you sort of go through this classification, and I just want to list them off and give some intuition for them. So we're doing fully fermionic phases, and the table is organized as following. Does there exist? Some question. This is the obstruction, and then this is the torsor. So this is the one we just reviewed. It's basically the bosonic obstruction that we have used to describe our fermionic obstructions. Now we want to recategorize everything. So the next obstruction you find is, so sorry, I got myself confused. Yes, the next thing you asked is, does there exist a localization of the symmetry action with a fixed global fermionic symmetry group? And that's what I'll refer to as OW. And when that vanishes, we have this H2 torsor, which is now valued in the abelian quasi-particles. The next question you can ask is, does there even exist a symmetry localization on the quasi-particles? And so that's some other obstruction, it's valued in the abelian quasiparticles modulo the fermion, and it has a torsor that looks like the following. Next question you ask is, does there exist a localization of the symmetry action on the quasiparticles with a fixed global symmetry group? So that's the analog of this question, but now just focusing on the quasiparticles. And then the last one you ask is, when there does exist a symmetry fractalization with fixed global symmetry on the quasiparticles, does that extend to the vortices? And that's this O eta obstruction, which is valued in H3 of G Z2 psi. And it turns out that can be interpreted in terms of some 3+1D fermion SPT. All right. When this vanishes, there's an H2 torsor, which can be realized by stacking fermion SPTs. Okay, so I've circled these last two obstructions because they're the most important, and they'll appear in the classification table, which I'll mention in 2 slides. All right, so since I'm running out of time, I will skip the algebraic description of fermionic G-cross braided tensor categories. It is morally the same as bosonic G-cross braided tensor categories with a few extra conditions. There are, again, consistency conditions, which look a lot like, well, they're the same as the Pentagon equation that we encountered before. And then there's a new one called the Heptagon equation, which tells you how to include symmetry actions on these particles. Okay, so what I'll mention is there is yet another obstruction you encounter when you go through the algebraic description of these G-symmetric theories. And this obstruction is valued in H4, and its interpretation is a failure for you to be able to solve the consistency conditions of this diagrammatic calculus, namely the Pentagon and Heptagon equations. And that obstruction only depends on the symmetry action, these phases U that we encountered earlier, and the symmetry fraction data, which we called eta. All right, when that obstruction vanishes, there's again a torsor, which is valued in H3, and it's related to stacking your theory with a G-symmetric bosonic SPT. All right, so on this slide, I have the full classification, and the left column is bosonic theories. The middle column is fermionic theories, classifying with respect to a fixed fermion modular tensor category and a fixed fermionic symmetry group. And the last column is classifying with respect to a fixed supermodular tensor category. Just that. Classifying with respect to a fixed supermodular tensor category and fixed fermionic symmetry group. Okay, so let me spend the last 2 minutes going through this column, and then I'll wrap up. So the initial data is a supermodular tensor category, M0, and a global fermionic symmetry group, which I remind you is a Z2 extension of G. We then compute our set of fermionic global symmetries for M0 and pick a homomorphism from G into those global symmetries. And this phi here is meant to represent that it's actually a projective symmetry action, but we decided to ignore that for this talk. Okay, so then we pick this rho 0, which is an element inside this set here. The next piece of data we choose is a fractionalization on those. So there's this obstruction O0, which is respect to a fixed fermionic global symmetry group. When that obstruction vanishes, we have a torsor valued in the abelian quasiparticles. And that tells us how to realize all other symmetry fractalizations. So the next step is to defectify, which is effectively the step I skipped in this talk, where you describe the algebraic data of the sort of braiding, statistics, and fusion of your anyons and defects. There are several obstructions that you encounter in doing that. One is the obstruction of lifting your symmetry action from the quasi-particles to the vortices. The second is the obstruction of lifting your symmetry fractionalization from your quasi-particles to the vortices. And the third one is the obstruction to there existing a consistent diagrammatic calculus of all the excitations. That's this H4 obstruction that I briefly mentioned on the previous slides. So once you construct one consistent theory, there is again a torsorial classification given by stacking with fermion SPTs. So these are G-symmetric G-symmetric extensions of K0, the trivial invertible fermionic phase. And then there is a Z16 torsor that comes from stacking the symmetric versions of the invertible fermionic phases with non-trivial central charge. And I'll just mention that the Z16 and the set of fermion SPTs can be combined into a larger group, and those will cycle you through all possible fermionic defect theories. All right, and I'll skip these slides and just say thanks. Sorry, I ran out of time. Are there any questions?
Yes, thanks, Dave. So, well, first, let's thank Dave, everyone. Yes, we have some time for questions. Before I ask my questions.
Well, very early on, I asked for an example, and you said it would be coming. But I only heard things which were rather general, and I don't. Can you give some specific model, like what you started with these? With this graph of Hamiltonians and so on, and just make concrete what these things really are, what the what the group G is, what the actual model is, what the elements are, and so on.
Yeah, so the only example I gave was this one, which was really just the modular tensor categories, not this G-symmetric version.
But what happened to the Hamiltonians and the graph and so on?
Yeah, I didn't do any of those examples. That we didn't even do those in our paper, but I know how to construct several. I do know how to construct those examples, but I didn't include them in this talk or our paper. I can send you a reference where that is done though. So if you're familiar with string nets, so a way to build a topological order from a fusion category, there's a direct extension of that to G-symmetric string nets. This was done by Lucas Witkowski, Fiona Burnell, and several other authors. And then there's a fermionic version of that, which hasn't been written in general, but if you're only interested in just a set of examples, there's some fermion SPTs, which have been constructed in the same way, using, again, G-graded fusion categories by Lakshya, Kapustin, and Gayotto. So I can put that reference in the chat if you like. But I don't have any of those examples in my talk. I was mostly focused on the anomaly picture. It's difficult which topics to choose. If you like, in our paper, we give several examples of fermionic G-cross braided tensor categories. I think it's the last section, or maybe second to last section. But they're not written in terms of Hamiltonians.
But maybe I can jump in for examples. But so, what would be the M1 for FQH state at filling 1/3? This is the vortices, right? That you mentioned. This natural extension.
Yeah, off the top of my head, I don't know. I'm sure it's been computed though. So the fusion rules of the 1/3 state are what? Is it Z3 times Z2?
It's abelian, and it has pi over 2 pi over 3 anions. Right?
Yeah, maybe it's Z6 then. So you take 3 of those guys and you get the electron fuses with itself to vacuum. So Z6 fusion rules. Yeah, I mean, it's I don't know it off the top of my head, but you could certainly write it down. We know all of the, for an abelian group, there's a systematic way to write down all the braided tensor categories associated with it.
And here the group, are you referring to the fusion group, or on top the symmetry group, because you have a U1 for charge?
Yeah, this is just for the fusion rules of the.
And the vortices physically, in that case, do you know what they would correspond to, or
like how you would introduce it in the system?
Anything, like how you think about them?
I don't know actually. So so like mathematically, it corresponds to a defect in your spin structure.
Mm-hmm.
And so if you were to introduce this non-bounding defect into your physical system, it would bind one of these vortices. How you actually do that physically probably amounts to thinking a special quantity of flux through the system. Not sure exactly.
Yeah, because if you introduce flux, then you'll bind fractional charge, flux. But that's not what you want, right? Because you want because the charge E/3 quasi-particle.
Well, the vortex could carry fractional charge. That's possible.
Okay.
Yeah, and in general, it will.
You can ask if there are any other questions, because I have one more question. Let's see. This natural isomorphism, that it seems rather important because it defines
very important.
equivalence classes, right?
Yes.
And
here.
Yeah, and then you gave some the definition of how it acts. Yeah, precisely here at the bottom. It seems very simple, almost trivial, but it's not. Can you tell us a bit more about the choice and how natural? What there are other definitions that would also be possible, and yeah, can you tell us more?
Yes, I don't know. I don't know if there are other definitions for this natural isomorphism. At least not that I'm aware of. What might look strange is this local fermion constraint. So in the bosonic case, you don't have this constraint, and it doesn't look so unnatural. But if you were to, as we did at the beginning of this project, start computing things without this constraint, you'll find many inconsistencies. Like there's a well-known result for stacking fermion SPTs with Z2 symmetry. You get a Z8 group. If you don't impose this constraint on the algebraic data, you end up finding, you find that it doesn't actually even form a group. So this, so one way you could rediscover this is by asking what is the minimal data you need to put into your G cross extensions such that you reproduce the known results. The way we justified this was not from that, of course. The way we justified it was thinking about what these fermionic natural isomorphisms mean in terms of the actual quasi-particles in the system. And those are closely related to these phases U that you pick up. There's again some constraints that you can derive on those. But yeah, maybe I can just direct you to my paper for more details. I actually have to go. I could put headphones on, but I have to bike to my next